you all. Thank you for the ones who have persevered and who are here for the third lecture. Maybe because or despite the first two, I'm not sure which. So the first one was about game theoretic testing, the second about game theoretic estimation, and the third is going to be about game theoretic change point detection. So I'm going to present two general frameworks for sequential change detection, with the focus is going to be on doing this for composite and non-parametric classes, because somehow most of the literature has developed it very, very thoroughly for parametric settings, but composite and non-parametric settings, there's not a unified way of doing things. There's like different people have studied different settings, but what I'm going to show you is a very unified way of dealing with non-parametric change detection. Okay, and we're going to need two key definitions that were there in the from the previous lectures, which some of you were there, some of you weren't. So I'll just recall the two key definitions we will need. The first one is that of an E process. Okay, so this is a non-parametric composite generalization of a likelihood ratio. Okay, so an E process is a sequence for a composite null that I'm testing, is a sequence of non-negative random variables whose expected value at any stopping time is less than equal to 1. Okay, and the simplest example we saw is if the null is actually simple, then all E processes are basically likelihood ratios, and we know that likelihood ratios are non-negative martingales, and by the optional stopping theorem, the expected value of the non-negative martingale at any stopping time is less than equal to 1. Okay, so for simple nulls, an E process is just a likelihood ratio, but the interesting part is that for composite and even non-parametric classes of distributions, we can construct these types of non-negative martingales and non-negative super martingales. And we saw a lot of examples last class of this exponential type of super martingales. We saw this product type of non-negative martingales for rich classes that don't even have reference measures. So this E process is going to be one definition that will come up very centrally in the talk. So try to remember it if you can. And then the second one that will come up very centrally is a confidence sequence, which we had used for estimation. And so I had kind of purposely developed the talk in these three ways, because first you do testing, then when you go to estimation, you realize that estimation is just testing in disguise, and then now when you come to change point detection, you realize that change point detection is just estimation and testing in disguise. And so we're going to use either testing tools, basically E processes, or we're going to use confidence sequences. And a confidence sequence is just a sequence of confidence intervals indexed by sample size that have a simultaneous or uniform coverage guarantee over all time. Okay, so that's what. So this is our key tool for estimation, and this was our key tool for testing. Okay, this is only two simple definitions. Okay, so now we're going to use this to do change point detection. But I want to give you one example of an E process to keep in your mind. And so because I didn't introduce this idea before, it's very simple and very generally applicable. So at least as a default go-to, you should think about this. So there's something called universal inference. It's a paper that we had in PNAS in 2020, and the E process that comes out of universal inference is some kind of weird mixture of Bayesian and frequentist ideas. So if you have a composite null and a composite alternative, then a Bayesian uses a mixture in the numerator and a mixture in the denominator. A frequentist uses maximum likelihood in the numerator and a maximum likelihood in the denominator. But we do something in between, where we use a mixture or a plug-in, one of those two, in the alternative, and we use maximum likelihood under the null. Okay, and the reason we do something like this, so the typical, so if you see something like this, Q is for the alternative, this theta hat I is going to be based on the first I minus 1 samples. So I call this an out of sample likelihood, so or a non-predictable likelihood. So you use the first I minus 1 samples to calculate theta hat I, and you bet on xi, and so this is like an out of sample likelihood, and this theta hat t is the maximum likelihood of the null of all of x1 to xt. Okay, so the parameter in the denominator is double dipping. It's looking at all the data and to calculate the maximum likelihood, and looking at all the data to evaluate that likelihood. And in the numerator, it's not double dipping. It's using I minus 1 samples to calculate the estimator and looking at its performance on the ith sample. And so the reason this is very interesting, this combination, is that this is an E process. But if you did it the fully Bayesian way, it's not an E process, and if you did it the fully frequentist way, it's not an E process. And so somehow, if you really want this E process structure, which means that at any stopping time, this is then you have to do this funky combination. And the key part is why is it called universal inference? It really works for any composite null and any composite alternative as long as you have likelihoods. As long as you can define a likelihood, this immediately works and gives you an E process. Of course, if it's a point null, this is just simply a likelihood ratio process. So it's very simple. But the key point is when you have a composite null, it's still an E process. That characterization property that we want is maintained over here. Okay, and so you can also show that if this, if you do something sensible for this plugin theta hat I, like if you use a Bayesian map estimator with a prior that puts mass everywhere, then it will have this optimal growth rate, which means that if the data is actually coming from Q, some alternative that you don't know, the expected log divided by t, this process, the way it grows is going to be as if you know the optimal Q. Like if you knew Q star, you'd just use Q star of xi over there, but you don't know Q star, but the growth rate that you get is still as if you knew Q star. So it's like you get the optimal growth rate, and this was only very recently proved by Ryan Martin in the arXiv paper. Anyway. If I think about it just as an E value, it's actually worse than the numeraire I presented in the first lecture. But the numeraire is actually just an E value. It's actually not an E process. This gives you an E process. And then, of course, if you invert it, you can get a confidence sequence also. So anyway, this is just one example. If you missed some of the earlier talks, this is an example of an E process you can keep in your mind. It's an abstract definition, and if you wanted an example of that abstract definition, remember the definition was the expected value of E tau is less than equal to 1 for all P in my null hypothesis and for all stopping times tau. So that's the definition of an E process. Okay, so yeah, we finished those two. Now we're going to change detection. And here's the super high level problem set. If you have not seen change detection before, it roughly works like this. You observe some data, it could be scalars or vectors or some objects one at a time, and you calculate some statistic of the data as you go along. Okay, it could be a Q sum or SR statistic if you have heard of these. And then you have some threshold, and then when the statistic crosses the threshold, you proclaim that there's been some change. Okay, that's going to be how it works. And maybe people are more familiar with type 1 error and type 2 error in testing. When you go to change detection, the corresponding notions are detection delay and false alarms. Okay, so the aim is to minimize the detection delay. That is, when there is a change point, how quickly do you find it, while controlling the false alarms, which means then when there's no change, how often do you proclaim there's a change? Okay, so more formally, here are the metrics of success. So the average run length or the frequency of false alarms is the analog of type 1 error from testing, and the definition is when there's no change point, the ARL is the expected number of steps before we falsely proclaim a change point. Okay, this is different from testing. In testing, what we wanted is that if the null is true, we never reject the null with high probability. But what's happening over here is every ARL number of steps, if ARL is 1,000, every 1,000 steps about in expectation, we're going to falsely declare that there's a change point even when there isn't one. Okay, so it's the expected number of steps before we falsely proclaim a change point when there's actually no change point. So let's say we are okay with some false alarm every 1,000 steps, that the ARL would be 1,000. And the detection delay is like the analog of type 2 error, where you say, well, suppose there is a change point at some time nu. The detection delay is the expected number of steps after nu that we need to correctly proclaim that we have found a change. Okay, so the reason it's defined in this way is roughly the following. You could have defined the type 1 error like we do in testing. It's saying if there's no change, then never proclaim a change. You can do that, but then it turns out that change. The detection delay will depend on the time of the change. So the further in the future the change is, the detection delay will actually depend logarithmically on nu. But with this definition of the average run length, in which you say I'm okay with making an error like every 1,000 steps, it will turn out that the detection delay need not depend on nu at all, the time of the actual change. And so, yeah, you can have other definitions of these two, but this is maybe the most typical in the sequential change literature. Okay, but the critical issue in practice is that controlling the average run length is very hard. Okay, so if the pre-change distribution is perfectly known, then it's completely easy to control the ARL. You can just run a simulation. You have some test statistic. You can simulate from your underlying distribution millions of times, and you can find how often it crosses some threshold or things like that. Or sometimes you can use analytical calculations, asymptotics, things like that to find the threshold. That's if you know the pre-change distribution. But you cannot do this if the pre-change distribution is only known to lie in some set of distributions, and typically some non-parametric set of distributions. So we might only know some partial aspects of the pre-change distribution, like we might know that the variance is smaller than some number, but not exactly what that variance is, and so maybe you don't know exactly what to simulate from. I mean, this is still maybe a simple case. You can say just simulate from variance 10 because that will be the worst case, but there will be other non-parametric problems we look at where there is no notion of a worst case distribution that you're trying to protect yourself against. So, we're going to look at problems which is somehow not amenable to setting the ARL by simulation. So if we don't know how to model some aspects of the pre-change distribution, like typically you have a non-parametric pre-change class, then like for example, if we know the data is bounded, but we don't know anything else, then you don't know what to simulate from. In such cases, it's actually much harder to control the ARL, and simulation and math don't easily work. You can't use asymptotics that easily with non-parametric classes, and you can't do simulation that easily with non-parametric classes. Okay, so I'm going to now, what I'm going to show you is two works that say, what I'm going to do with sequential change detection is I'm going to just reduce it to the problem of sequential testing or to the problem of sequential estimation, because I know how to do those problems really well. In non-parametric settings, I know how to do those well, so like why don't I try to do the same thing here. Okay, so the first one is called an E-detector, and was just recently appeared in a New England Journal of Statistics and Data Science, and the second one is that's using testing, and this one is using confidence sequences, and that's on arXiv. Okay, so why are there two reductions? That's because there's actually two settings of change detection that are of interest. So the first setting is what I call separated change point detection. I don't know if that's the right word for it, but essentially where you know the pre and post change classes ahead of time. I tell you that the pre-change distributions lie in some class script P, and post-change distributions lie in some class script Q. Okay, so it's like, so for example, I tell you that it's Gaussian, the data is Gaussian, and pre-change it has negative mean, and post-change it has positive mean. And I said these are like distinct classes I define ahead of time, and it changes from something in script P to something else in script Q. So they're both classes of distributions, but it changes from something. So this I call separated change detection. In the other cases where the pre and post change distributions are unknown, but they come from the same class. So I just say the data is Gaussian and the mean changes from something to something else. Maybe it changes from -5 to +5, or from +5 to -5, or from -2 to +2. I don't know. It just changed from some A to some B. There are no separated classes P and Q. It's just one class, and it changed from something to something else within that class. Okay, so this is the non-separated change point detection problem. Okay, so what we're going to do is, for this first problem, we're going to reduce change detection to repeated sequential testing of P versus Q, and in the second case, we're going to reduce change detection to repeated sequential estimation using confidence sequences. Okay, and so the method at a high level, I'm going to go into details now. This is a high level picture, but the method is at every time step T, we're going to start a new sequential level alpha sequential test based on xt plus 1 and so on. So at time step T, we have seen T minus 1 point so far. We start a new sequential test from time step T onwards, but we're going to do this using an E process. That's going to be the key novelty. I'll come to this later, and we're going to declare a change when our accumulated evidence from this E processes crosses 1 over alpha. Okay. And in a confidence sequence, we're also going to do something similar. At every time step T, we're going to start a new confidence sequence from time step T onwards, based only on the data xt plus 1 and so on. And we're going to declare a change when the intersection of all of these confidence sequences becomes empty. Okay, so if I find some contradiction, I'm starting many confidence sequences over time. If I find a contradiction, I declare a change point. And the key part for both of them is I will show that both of them, the main theorem is that you completely generally you can prove that the average run length is at least 1 over alpha, and the same thing in this case. So no hidden confidence. If these are 1 minus alpha confidence sequences and these are E detectors, E processes that I'm using under the hood, then the ARL is non-asymptotically controlled at level 1 over alpha. And the second part, which obviously you have to talk about as well, is that somehow you do get optimal detection delays in both settings, but I'm going to focus, my notion of optimal is going to be somehow focusing on the first order term, which should look like log 1 over alpha divided by some kind of a KL divergence, but you have to be more careful in non-parametric settings what that means. Yeah, so this is the rough outline of the talk, and now I'm going to first focus on the first case, where we're going to first discuss separated change point detection, then I'll discuss non-separated change point detection. Okay, so we'll first talk about this problem. Okay, sorry, there's something at the bottom that I forgot to say. Yeah, so okay, that's fine. Okay, so partition change point detection into sequential testing, reducing non-partition change point detection to sequential estimation, and then I'll end the whole thing with a high-level summary of game theoretic statistics overall. But the actual part of the talk is the first two. Okay, so this is joint work with Jae-Hook Shin, who was my PhD student and is now at Google, and Alessandro Rinaldo, who was at CMU but is now moved to UT Austin. And TLDR is you can reduce sequential non-parametric change detection to modern sequential testing using e-processes. Okay, to set the stage, I'm going to recap a method by Lorden in 1970, which has the right intuition, but you know, there's much more to say than what he did. We can improve, essentially what we have is an improvement of Lorden's method. So what Lorden said was the following in 1970. Okay, so he said, you know, so suppose you have a one-sided level alpha sequential test of P versus Q. So he says, you know, you're doing change detection, but I can first, it's from P to Q, script P to script Q. But the first question I can ask is, can I even test from whether you know, all of the data comes from script P or all of the data comes from script Q? Can I do that test? Okay, so suppose I have a one-sided level alpha test. So one-sided means that under the null, I should never reject with probability alpha, and under the alternative, you want something like power 1 under the alternative. So this is like under like Robbins' kind of framework of power 1 test, but it's like a one-sided test. You want a guarantee of type 1 error control under the null. So what he said was, so for each t, after seeing xt, we are going to output a 0 or a 1. Okay, 0 means there's not enough evidence to reject p, and 1 means we have enough evidence to reject p. And a level alpha sequential test is just the probability that if the null is true for any p in script p, if the null is true, the probability that you ever stop and reject the null is at most alpha. So we constructed a lot of sequential tests in the first lecture using e-processes, but in his case he just says, assume I have a level alpha sequential test for this problem. Okay, so Lorden's reduction is at every time step t, start a new level alpha sequential test based on xt plus 1 and so on. So after t steps, there are actually t sequential tests running. One of them looked at data from x1 to xt, another one looking at x2 to xt, another one looking at x3 to xt, another one looking at x4 to xt. So at time step t, there's t sequential tests that have started so far, and he said we can declare a change when any of these sequential tests rejects the null. So if any one of these sequential tests rejects the null, we'll declare a change point. Okay, so it's a reduction from change point to testing. It says if any sequential test rejects the null, we'll declare a change point, and he proved that this method controls the average run length at level 1 over alpha. Though there's some caveats, he really needed the data to be IID because of his proof techniques and things like that, but it's somehow the nice idea. And the TLDR of our paper is we have a more sophisticated reduction to sequential testing, which shouldn't use sequential tests, which are 0-1 decisions, but should use e-processes instead because they are evidence, and you can actually accumulate the evidence across various tests. So instead of here like somehow all the burden of evidence is on one test, because if one test rejects, I can stop and declare a change point. But somehow if I can accumulate evidence across the tests, then I can stop sooner. I can have a smaller detection delay. And so this is a uniform improvement of, like what I'm going to present is a uniform improvement of Lorden's reduction. It's still a reduction to testing, but it's a better reduction than this one. And it holds more generally. So the ARL control that I'll present holds more generally than Lorden's. Yeah.
So which paper do you refer 1970? Is 1971 or 1970?
Maybe 71, okay, maybe I'm yeah. Whichever one has this, an Annals of Statistics paper or something which has this reduction in it. 1971, yeah, okay. Thank you for the typo.
Exactly,
yeah.
50 years ago.
Yeah, exactly. 1971. I don't know. It's cited in my paper, so you can check in the e-detector paper. You'll see the citation there. 1971. Yeah. Okay. Yeah.
So suppose that happens. You're not improving anything.
I'm still improving things here. I'm going to stop. I'm going to give a better reduction to sequential testing. That's going to be better than this. It's going to stop sooner. It's going to have the same average run length control at 1 over alpha, but the detection delay will be smaller.
Oh, got it.
Yeah. So the ARL could be the same, but detection delay will be small. Okay. Okay. So the method is called an e-detector. Okay. So let's lots of E over here. So let me define the e-detector formally. So script P is our pre-changed set of distributions over infinite sequences. So not IID. So a single draw from P is I get an infinite sequence of data x1, x2, x3, which need neither be independent nor identically distributed. It's just some pre-changed set of distributions. Okay, so it's a set of distributions, and each distribution is a distribution over infinite sequences. So it does not have to have product distributions or something of that kind. It's just some set of distributions over infinite sequences. There's the choice of a filtration. This is actually, I'm not going to talk about it much here, but the filtration that you work in need not be the filtration of the data. So it turns out that there are actually many problems, especially ones involving nuisance parameters, where you actually want to restrict the filtration and actually work in a reduced filtration. But for simplicity, if you don't even know what this statement means, just think of the filtration as being the filtration of the data. Okay. So what is an e-detector? E-detector for script P is a non-negative process M such that the expected value of m tau is less than or equal to the expected value of tau, and that should hold for any distribution P in my class script P and for any stopping time tau. That any stopping time tau with respect to this filtration, but fine, if you just ignore, if you take the default filtration, then it's just any stopping time tau. Okay, so if you remember the definition of E process, it's a sequence of non-negative random variables where the expected value at any stopping time is at most 1. Now I have a non-negative process such that the expected value at any stopping time is the expected value of tau. Okay, so it's something different. It's not an E process, it's an E detector. Its purpose is different. Sorry, yeah. So why this? If you are able to construct an E detector, you get non-asymptotic ARL control. So you stop at the first time that your E detector crosses 1 over alpha. Like earlier, if you were doing sequential testing, we stopped at the first time that the E process crossed 1 over alpha, and we got type 1 error control. Now we stop at the first time that the E detector crosses 1 over alpha, we get non-asymptotic ARL control. So if M is an E detector for script P, then the ARL of this stopping time, the expected value of the stopping time under any null. So for any null, meaning any pre-changed, by say null I mean any pre-changed distribution, if the data is coming from any pre-changed distribution, the expected value of my stopping time is at least 1 over alpha. That's what it means to control the average run length. Means that when there's no change, you should stop at least every 1 over alpha steps. Okay, so you get this non-asymptotically cleanly as long as you can define, as long as you can define an E detector. Any E detector satisfies this constraint. Okay. So the question is, how do you construct an E detector? And the answer is actually very simple. So I'm only going to talk about this one. We have a QSUM one in the paper, but I think for this is the right one to focus on now. So we define the SR. SR stands for Shiryaev-Roberts if you're in the literature, but otherwise just think of it as a short form. So it's a SR E detector. It's the sum of E processes started at times j. So essentially what I'm doing is at each time j, I'm going to start off a new E process. Instead of starting a new sequential test like what Lorden did, I'm going to start a new E process. Okay. And I'm going to accumulate the evidence from all of those E processes. Okay, so this lambda j is an E process that started at time j. It doesn't look at data before time j, but from time j onwards, it's an E process. So it's essentially testing the null of script P versus script Q, but it's not making a decision of 0 or 1. It's just accumulating the evidence against the null. Okay, so rather than like what Lorden was doing in this language is he was summing up things that were binary, like in some sense either 0 or 1 of them, and if any one of them crossed rejected the null, then he was able to. But what I'm doing instead is I'm accumulating evidence across tests. So no individual test may have reached level 1 over alpha, but the sum of these various tests that I've started that might still cross 1 over alpha. And so it will stop much sooner. So you can easily actually show that Lorentz is a special case of this. But the key point is it's a special case in a very degenerate way. If your sequential test takes on only 2 values, 0 and 1 over alpha, then you get Lorentz. But otherwise, if you use e-processes, each of these will be non-negative. Remember, e-processes are non-negative. And so I'm summing up many different non-negative things. And so whenever it crosses 1 over alpha, it's very likely that the individual things did not cross 1 over alpha. It's just that the sum crossed 1 over alpha. So I could not have rejected each of the individual tests. None of the individual tests rejected, but their sum showed me that there's enough evidence to that I can stop and declare a change point. Okay, so this definition of an e-detector is key. And yeah.
I can add a comment. So normally in the Q-sum, the MT researchers in the sequential changing point seem to just replace the sum by the maximum.
Yes, yes. So in the I have that in the paper. Yeah, but the reason is but this somehow this threshold is the right threshold for in the SR scale, but for the Q-sum, yeah, I don't know what the right threshold is because we're in a parametric setting. So like we have some class of general distributions, and so yeah, it's like anyway. So I'll just talk about SR right now over here. Yeah.
I'm struggling to parse the definition of e-detector.
Yeah.
Is the right way of thinking about it is essentially like this, like
yeah.
Yeah, it's just
Yeah.
summing all these things from 0 to
exactly.
Okay.
Yeah, right. Yeah. It's actually not. Neither of these is obvious. The fact that this implies this is not obvious. It's a short proof, but it's not obvious. The fact that this satisfies this is also not obvious, but it's a short proof. So that's right. Yeah, but essentially because I'm summing e-detectors, the expected value isn't 1, but it's how many I've started.
Okay.
Yeah. So I mean, it's clear that at any time n, it's clear that the expected value of this is at most n, but it's also true at any stopping time tau. Yeah, and that's because of e-processes being nice with stopping times. It works out. Yeah.
You can't use like the optional stopping theorem again.
Not directly. Yeah, that's
because
right.
e-process is more general than supermarket.
No, e-processes also satisfy optional stopping. They do. Yeah. So that's a definition. My definition of an e-process is that at any stopping time tau, this holds. So like that's like saying I've optionally stopped it and I still get something. Yeah. But it's just that over here, if I have a sum over tau thing. So it's like for an e-detector, I can't directly apply optional stopping. If I look at its value at time tau, it's the sum over tau things of e-processes. Each of these e-processes you can apply optional stopping to, but I have a random sum of them. So you just have to be a little bit careful, that's all.
So can you also clarify when you say the pre-change set of distribution over the infinite sequence, are you assume the data are an ID?
No. So no, that's the key point again over here. There's two aspects of it. First aspect is it's a set of distributions, meaning it's the pre-change is not a known distribution or something, it's some set of distributions. The second thing is every distribution in that class need not be a product distribution. It could itself be some non-IID distribution over infinite sequences. And I'll give examples, I guess, of this. Yeah.
One comment I want to add is that when the data are not IID,
Yeah.
even if they are independent,
Yeah.
but not identical distribution under the
Yeah.
non-hypothesis, sometimes the average run length, the criteria itself could be questionable.
Yeah, I know you have a paper on this. Yeah, it would have been nice to talk after this talk, but yeah, I've seen your paper on this. I agree. Yeah, yeah, but I'll show you examples where I think it still does make sense. I mean, it's not completely IID without any control, but there's some sense in which some part of it is stationary and some part of it is not, and I'll show you some examples. Okay, it might seem like this e-detector computation is blowing up with t. That is because I'm starting a new e-process at every time to t. I have to track so many things over time. But there's many cases in which you can compute things fast. So often or sometimes our e-processes can be written like a product of these types of terms. So it's just like this exponential super martingale structure that we saw in the last class. It's just a product of these terms. So when the e-process can be, and each of these is just an e-value. So like we saw this as 1 plus lambda times xt minus m when we were betting, or we saw this as exponential of various things if we were doing this non-parametric stuff last time. So this often happens. So when this happens, just like the Shiryaev-Roberts procedure, you can compute our e-detector in an online fashion. So this really is remember every time I talk about e-processes, I'm trying to use likelihood ratio type ideas in settings where likelihood ratios are not well defined. So e-processes are non-parametric generalizations of likelihood ratios. This is the formula when everything is likelihood ratio based in the Shiryaev-Roberts procedure. You'll see exactly this recursive formula, but we are trying to do it in settings where even an MGF may not exist, or you don't have a reference measure, but you can still define and construct these things. And somehow the key property is like the math never depended on anything got to doing with likelihood ratio. Somehow all we really needed was the non-negative martingale structure, or the non-negative super martingale structure, or actually the e-process structure. All we needed was the e-process structure, and everything still does go through. That's somehow the key observation, which allows us to now handle non-parametric problems. So of course, when you have likelihood ratios, it's a point null, but you can instead work with non-negative super martingales. And even as we saw, even non-parametric settings where you don't even have an MGF. Okay, so let's look at an explicit example to see how you would construct it in practice. Okay, so this is a setting where this is data from the NBA, the Cleveland Cavaliers, across 8 years. Okay, and every dot is one game that they played across this 8-year period, and this is split into seasons. So these blocks that you're seeing are, they did not play anything in the off season. So this is really, you know, time ordered by months, by games actually. And so there are 8 seasons going on over here. Every dot is a game, and it's the plus minus of the Cavaliers. Meaning in that game, how many points did the Cavaliers score minus how many did they concede. So of course, if it's above 0, it means they won the game, and if it's below 0, it means they lost the game. And here clearly they got thrashed in the game. So anyway, that's, you can kind of see that. So that's how they performed. So now one question that you might ask when you look at this is, okay, you know, if I'm observing this sequentially, I'm showing it to you as a batch, but suppose you're observing this from left to right, can you declare, is there a change point at some point from a negative plus minus to a positive plus minus? So remember this, in this case I'm looking at the partitioned problem. I'm telling you script P beforehand is something with a negative mean, and after what I'm trying to detect a change to is something with a positive mean. I'm telling you this beforehand in the partition case. So I'm going to ask you here, is there at any point, is there a change from a negative to a positive plus minus? Okay, so clearly in this problem, the future is not independent of the past, and it's not identically distributed. So I don't want to make any kind of IID assumptions in this kind of data. So I really want a non-parametric way of detecting a change point in such a setting. Okay. And so, yeah, so this there is related work of people who have talked about non-parametric change point detection, but what I feel like the main contribution here is just a unified way of doing all of non-parametric change point detection in these types, in any partition setup. So the main challenge here is this plus minus stat of a random of a game is just a bounded random variable between minus 100 to plus 100. You can rescale it to 0, 1 to simplicity. And its mean varies over time, maybe even its variance varies over time, I don't know. And you know, the mean might vary with form or injuries or things of that kind. And we know nothing else about the distribution. Like anybody who tells me the distribution is beta or something else, I'm going to question them. It's some weird distribution, it's changing somehow. I don't want to make any assumptions. So here's how I'm going to cast the problem. So I'm going to say that x1, x2 and so on, they're not coming IID from P. P is a distribution over infinite sequences. So it's a joint distribution of x1 to x2 for some P. So this is pre-change, this is what's happening. And script P is just set a distribution on 0, 1 to the infinity such that the expected value of xn given whatever's happened so far is less than equal to a half. So I'm just rescaling from minus 100 to 100 to 0 to 1. So when I'm saying negative to positive plus minus, I'm saying that they're losing more than half the time to winning more than half the time. And so that's why the half over here, but it's just on 0, 1 to the infinity. So every game I see something between 0 and 1, less than a half means they lost the game, greater than half means they won the game. And I'm asking at each point it's just non-IID structure, but they're more likely to lose the games. And then script Q is joint distributions on 0, 1 to the infinity such that the expected value of xn given the past is greater than a half. So they're more likely to win the game. So so if there's a change point at time nu, then the data after nu, x nu plus 1, x nu plus 2, blah, 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 that's a joint draw from some q. Okay, so this is how I'm going to model things as no I or no ID. None of those are true, but I think the question still makes sense. Did they go from a losing team to a winning team, and can I detect that change? Okay, Yeah, so anyway, so that's, and the only restriction is on the conditional means. There's nothing else known about the distribution, that's why it's non-parametric. Okay, so, yeah, okay, so the method we have, yeah, 1 second. What do I want to say? Okay, yeah, so this was the, anyway, this is not the method, this is just the problem statement I'm trying to say. So for now, just imagine that you know there's a fixed Q that it's changing to. So remember that it's like a composite alternative. To deal with the composite alternative, we'll mix or we'll plug in. So let's now answer the question of a fixed Q. Okay, so if I know what the alternative is, it's changing to some particular distribution with mean greater than 0.5, then we saw from the previous 2 lectures, but especially the previous one, in which this kind of a process is actually the optimal non-negative super martingale. It's the numeraire if you saw the first lecture. Otherwise, if you saw the estimating means of bounded random variables by betting, I'm testing if the mean is less than or equal to a half. The optimal super martingale for testing this is actually the product of 1 plus lambda times lambda star times x minus half, where this lambda star depends on Q. And we looked at 2 methods like this grappa method and things like that, but there is an optimal lambda that so this is a non-negative super martingale. It has also this product structure, so you can just plug it into the E detector. I have an E process for testing script P versus script Q, because this is like the bounded mean test that we had last lecture. So as long as I have an E process, this is an E process, it's a super martingale, I just plug it into the E detector and I'm done. Okay, so that gives me what I want. So this is what we do. So we also mix over Q. I'll get to that soon. But you run the E detector, and this is, I'm showing you on the log scale now. This is log 1 over alpha that it had to cross. And so the E detector just was doing something, and then it spikes up at some point in the 2014-2015 season. It crosses the threshold, it continues to increase. You get more and more evidence, perhaps, if you think about it that way. But anyway, there was a change point. That's the point at which we declare it. This is a nice setting because actually we know that in this 2014-2015 season, LeBron James joined the Cleveland Cavaliers. So it actually, we do think there was a change at that point. But the point is, if you're monitoring it from left to right, you can declare a change at that point. Okay, so and this method we set 1 over alpha to be 1,000. So this controls the average run length at 1,000, which is more than 12 seasons of games. So this is only 8 seasons. So like we had set our ARL large enough so that it's more than 12 seasons of games, the expected time that we. So if you're stopping somewhere in the 5th season, you think maybe it's actually a reasonable. And we think the detection delay is quite small because the change happened after the 2014 season ended, and so we're detecting it somewhere halfway through the new season. So kind of makes sense. Anyway, the point is, this is a non-parametric, non-stationary change point detection problem, but you can cleanly and easily solve it just by reducing it to tools that we covered in the previous lectures. Yeah. Yeah. Yeah.
What is the detection specific?
So what is the detection what?
Detection specific. You're running this procedure, right? So
it's the E detector,
yes,
which is the sum of E processes.
yes.
The E processes are these ones.
This is xt minus 1/2.
Now this was sadly you missed the previous lecture, but this was a non-negative super martingale, for the class that for this class. So if the conditional mean is less than a half, then this guy is this is a non-negative super martingale for that class. And
I'm just wondering that specifically
yes.
when I apply the data in here,
Yes.
what is the xt and what is the non-negative?
XT is the outcome of the game, the plus minus stat of that game, which was not plus minus 1. It was this between minus 100 and plus 100, the point difference between the Cavaliers and their opposition. So the data is, this is the data. This is XT. I'm just rescaling it to 0, 1. This is minus 100 to plus 100. I'm rescaling this to 0, 1, but that's XT. And the half is going from a losing team to a winning team because I scaled from 0 to 1. So yeah, the thing I'm looking for is whether the team went from a losing team to a winning team at some point.
Is this like a one of the references is like self-normalizing process.
Yeah.
You're still
But in this is not a self-normalized one. I can apply, but this particular one isn't self-normalized. I don't need, so self-normalization is a tool to deal with heavy tails. This doesn't have heavy tails. Because it's a bounded distribution, it has light tails, but I want to be variance adaptive. So I want to get like the optimal behavior, not just, even though I'm trying to detect a change in the mean, what I would like is if the variance is small, I detect faster. If the variance is large, I detect later. So like I want a behavior of the detection delay that's adaptive to the variance of the distribution. I mean mean also, if there's a larger mean shift, I want it to stop sooner, but I want a behavior that depends both on the mean and on the variance. And so that last lecture we kind of discussed why this kind of a process you should view as an empirical Bernstein process, which is getting both mean and variance behavior.
For this particular data,
Yeah.
empirically, do you observe the shift in mean, the variance, or the third moment or something?
Oh, I'm only trying to detect a difference in the mean, and somehow like for a bounded random variable, it's really the variance that's the most important part. Variance is a nuisance parameter. I don't care about its change, but it's a nuisance parameter that affects the optimal rate of detection. So essentially, if the variance of this data had been smaller, I should have been able to detect faster. If the variance is larger, I should have been able to. I'm trying to detect the change in the mean. The variance is a nuisance, but it determines the optimal rate. So I want a method that's adaptive to the variance and to the mean, even though I don't care about a change in the variance. So if you look over here, it doesn't seem to me like the variance is changing. We don't make any assumptions about anything about the variance or anything about the distribution. So we're only trying to detect a change in the mean. But if I look at it, it seems like the mean has shifted. The mean shifts in every season, but it has shifted across the 0 mark in this 2014 to 2015 season. But it doesn't look like the variance has really changed much. So, but that fact is irrelevant. Like the method controls the ARL independently of, even the variance could have changed, it would have still controlled the ARL, and if the variance became smaller, it would have controlled the ARL and stopped very early also. And if the variance became larger after the change point, then it would have controlled the ARL and it would have detected a little slower. So somehow the stopping time or the detection delay is a function of the mean change and the variance for this problem. That's the optimal answer depends on both. So it's really weird, like somehow the optimal, but this is true for a Gaussian mean change detection also, like the optimal answer for a mean change depends on a nuisance parameter as well. And so what we want is, we want this kind of optimal behavior in both the main parameter and in the nuisance parameter.
So your framework is that you have a single P in the script P, and then you're moving to a single P
No,
in the script P.
it actually can
move around with
yeah,
P.
exactly, yeah. So because P is not IID, so because P is not IID, it turns out that this class is actually already a convex class. So like any mixture of things over here is also in the same class. Exactly. So yeah, these kind of moving between things in P is allowed already. By definition of script P, it could have been different distributions in different species. That's fine with me. It controls the ARL regardless. And same with script Q. I'm not, after it's changed, it could change per season because the post change class is also convex. In fact, it's what's called fork convex, in the sense that, like, fork convex is the idea that you follow Q1 up to some time, and then you follow Q2 after that time. That gives me a new distribution. It's like I've changed the distribution at some point. You can ask, is this distribution in my class? And these two classes are also fork convex, in the sense of convexity is a concept of just mixtures, which means with some probability I follow Q1 and with some probability I follow Q2. Fork convexity means I can fork halfway from Q1 to Q2. And not just once. I can do this like a convex class means I can do this however I want. And so fork convexity is the sequential analog of convexity that says I can go from Q1 to Q2 to Q3 to Q4. I can do these shifts and the class is closed under focus. So this is actually a fork convex closed class. And so it allows this kind of interesting non-stationary adaptive movement. So in fact, that movement can even be adversarial, which means under the null, if there's under the pre-change distribution, an adversary can be telling me at every step what, as long as it maintains this condition, it can change the distribution at every step adversarially, no problem. So it's like really a strong guarantee on average run length control, and actually it doesn't matter for detection delay also. It's the same thing, yeah.
Can you comment on the impact of the threshold of -40 of or 40, will that have an impact on your performance?
So our threshold is
will not change the value for x, but will that change the value for lambdas?
sorry, what is?
It's threshold minus 40 and 40 when you normalize to the 0 and 1.
Oh, actually, we assume it's minus 100 to plus 100, but it doesn't matter. It doesn't matter too much. Yeah, what's the right way to say this? It has, yeah. If I squash the data, which means I could have assumed minus 50 to plus 50, I could have assumed that, but actually I'm doing more conservative and saying in every NBA game in history, there's never been more than a 100-point difference between the teams, so I assume it's minus 100 to 100. But the data is bounded within a smaller range, it's going to have a small variance, smaller than my worst case bounds predict, but my bounds are adaptive to that variance, so I don't really pay a price. So essentially, if I was using a method that really depended on the bounds and worst case depended on the bounds, I would be screwed. But I have a method that automatically adapts to the variance. So when I have larger bounds, I'm basically saying relative to those bounds, actually I have a much smaller variance and my method is variance adaptive. So I don't actually pay for those bounds. Actually, more formally, you pay a log B. If the data is actually in minus 1 to 1, but you say it's in minus B to B, you'll pay a log B price at some point. But in this case, that's going to be a log 2, which is really small, so it's not, doesn't really show up.
I actually want to look at the other way around for the NBA game based on I'm an NBA fan.
Yeah.
Look at it. So if it's above 20 or for minus 20, then it's bench player played the fourth quarter and so on. So probably
maybe
not that indicative. I would more look at the figure out if it's difference too much, that has a little impact.
Yeah, but this is more a representative application. Now, if you're really in the NBA, maybe you will remove some outliers, I don't know, or you'll shrink towards mean, I don't know. But like, this is just to show you how to apply the e-detector for a problem that we don't currently know how to solve. Okay. So more, yeah, anyway, so I think I said this several times. So let me give an example of new settings for which we can now do change point detection using new e-processes. Okay, so any script P for which maximum likelihood is actually feasible. So an interesting one is shape constraints like monotone or log concave. So you might say my pre-change distribution is monotone and my post-change distribution is not monotone. Yeah, we can now do that. We have a change point detection for that problem now because universal inference gives us a test of monotone against not monotone, an e-process in particular. What about log concave? You can say my pre-change distribution has a log concave density, my post-change distribution is not a log concave density. That's great. We have an e-process for test for log concavity, and you plug that in and you get an e-detector for that. So these are new problems for which there are no existing, well, there were no existing sequential tests for these either, but now there were also no existing sequential change detection methods for shape constraints of this kind, but now it just cleanly, you have your e-process from universal inference, you plug it into the e-detector and you can solve it, and that's great. Here's actually a very interesting one. The pre-change data, all I claim about it is that it's exchangeable. It's very interesting. It's a very rich class. Like I'm not saying anything else about it actually, nothing else. I don't even know the domain. It's just some exchangeable data. So script P is a super rich class and script Q is unrestricted. Let's say script Q is Markovian distributions or something. It's not exchangeable and maybe they have a Markovian structure or they have some kind of AR1 structure or something else. Then again, same thing. It turns out you can apply universal inference type ideas or you can apply conformal prediction type ideas to construct test martingales. You can plug them into the e-detector and they give you change detection for this very interesting pre-change and post-change class. Okay, here's another one. This is two sample testing. Okay, so here the pre-change you have two streams of data in the pre-change. Okay, you have two streams of data and your statement is in the pre-change view version of the world, the two streams of data have the same distribution. And after a change point, those two streams of data have a different distribution. Okay, super non-parametric. This is literally for any P, discrete, continuous, any support, doesn't matter, I don't care. My null is just P cross P to the power infinity. This could be multivariate P, it could be images, whatever, anything. But all I have is, yeah, just pre-change 2 streams of data from the same P, and then post-change it has somehow changed. It somehow P is just now not equal. Now I have 2 different things, and the P need not be the same before and after. So after the change, both the original distributions could change, but they change to different things. So now we have an e-process for this this is an IEEE transactions of information theory paper in which we have a non-negative martingale for this problem that is consistent against every alternative. So with no assumptions under the null, it's consistent against every alternative. So when you plug that into an e-detector, you get something that's an average run length control at 1 over alpha, and if it did change, you will detect the detection. You will, no matter what it changed to, you have no idea what's going on, you will at some point stop and detect declare a detection, and I can characterize that detection delay, but maybe I'll get into that a little bit, but not too much at the moment. But yeah, so you can do this cleanly now. Yeah.
Question. This is maybe a bit pedantic, but going back to your previous
Yeah.
example of P and Q, P being exchangeable and Q being unrestricted. Strictly speaking, there's no sense. I mean, unrestricted includes states of exchangeability. So
No, yeah, I guess I really mean unrestricted outside of script P. But you have to be a little bit more, you have to be more careful about it. But I would say, like that's why I said think of Markovian, or think of, you cannot have power, in this case you cannot have power against every script Q. But you can have power against, for example, all Markovian processes. So Markov of first order, second order, third order, fourth order, things of any order, if you define that to be script Q, I can have power against, which is not exchangeable, I can have power against that. Or if you define it to be AR1 or AR2 or AR3 or AR4 for any order, I can have power against that script Q. So very, very rich script Q, and you have no idea what order the AR is or what order the Markov is, that's fine. You can still define e-processes that are like for testing valid, meaning if the null is exchangeable, you'll never reject the null with high probability, and if the alternative is Markov of any order, you will reject it with probability 1. I mean, it's a power 1 test, and I can tell you I can tell you stopping times for when you'll reject it too. So you just plug that in directly to change point, and you get the corresponding guarantees for change point. So here's a different problem. So now you have heavy-tailed mean change detection. So the pre-change class is, let's say, all distributions for which the mean is less than mu and the variance is less than sigma square, but I don't have higher moments, but I know sigma square. And the post-change is the mean is greater than mu, the variance is still less than equal to sigma square, something like that. Okay, so but now these are just heavy-tailed distributions. I don't know anything about them. They could be discrete or continuous. So again, I don't have reference measures for these classes because I'm not assuming that they have a density or anything of that kind. So all of those examples, actually, I don't assume there's any reference measure. So that's fine. So we have developed non-negative super martingales for this problem. They plug into e-detectors. What about robust sequential change detection? So let's say you're in this setting, but so in the pre-change distribution, you know that the mean is less than some mu and the variance is less than some sigma square. So let's say 0 and 1 or something like that. But now an adversary can come in and arbitrarily corrupt epsilon fraction of the data. Okay, so this is the Huber robustness model where the data is coming from some such P, but then at some point an adversary can come in and say with probability epsilon, an adversary can come in and change your data to something completely different. Arbitrary, that's fine. It turns out that for this problem too, we have I have to remember now, this is an AI stats paper last year that shows how to derive these kind of Huber robust non-negative super martingales. So you can do Huber robust sequential change detection in this very general setting, no reference measure, weird adversaries, but you still get non-asymptotic control of the average run length, and you can bound the detection delay. The last example I'll mention is independence testing, where you're observing pre-change a pair of x and y. So x and y can lie in different spaces. So it could be images and captions. Okay, so essentially something like that kind. You're observing x comma y, and pre-change actually x and y are independent, and then at some point there's a change, and then post-change x and y become dependent, and I have no other assumptions on x and y. So again, could be discrete, continuous, reference measure, nothing. So this is called non-parametric independence testing in the testing world. And so we have at ICML last year non-parametric, non-negative martingale for independence testing. You can plug that into the E-detector, and now if you ever change from independence to dependence, you can detect it and stop and control the average run length and so on. So just these are examples just to get your mind thinking about weird problem settings in which we did not have ways of, or at least general ways of doing sequential change detection, but now the same one framework of E-detectors gets all of these problems for you in one go. Yeah.
I'm very interested in the second one, the cohort robust composite synthesis.
Yeah.
This one. So in that case, how do you define? Will you the average run length, those constraints, you are taking into account
Yes.
the corruption?
Yes. Then the reason is because that for this null script P, like in the testing problem, I can define a Huber-robust non-negative super martingale for this class. So this class is an epsilon total variation ball around this class. So somehow you take this class, I can define non-negative super martingales for that class. This class is an epsilon total variation ball around the other one, and somehow I can define a non-negative super martingale for this class too. I mean, it's an interesting one if you look at it goes back to some ideas by Catoni. This Catoni defined certain influence functions to handle heavy tail distributions, and it turns out that at one extreme of his influence functions, there's a certain clipping thing which makes you robust. So I don't know, it's interesting, but you can define Huber robust non-negative, so very simple ones, meaning they don't have a very complicated form. I mean, the super martingales are actually of the form of the form I talked about, where except it looks like the sum of I is equal to 1 to m some phi I of xi minus m minus some, let's say, lambda square by 2 times some variance process. So it looks a lot like the exponential super martingales I presented earlier, except over here I don't have a sum, I have a clipped sum. This is an influence function, a particular function, influence, this phi I looks like this. So it's not linear. If phi I was the identity, I would have just had my sum. But now I have some kind of an influence function that clips things, and so it's a very simple expression for these non-negative super martingales in the Huber robust case, and then there's an epsilon term that appears here as well. So you have to just adjust it by epsilon, and it turns out that it's still a non-negative super martingale. So it's very simple, but yeah, we've done it in another paper for sequential estimation or sequential testing, but you plug it in here and you get it for change detection. Okay, so what exactly can we say about detection delay? We have more in the paper, but I'm going to try and simplify things for the talk. So, for any change point fitting rule n, you can define the worst case detection delay as the sup over nu. Nu is the time at which the change point occurred. So remember, in some sense, we don't want it to depend on when the change occurred. So you can, okay, sup over nu, and this expectation p nu q means it's some p from script p before nu. Then at time nu, it changes to some q from script q after nu. So that's what EP nu q means. And this is, well, you stop, given that you stop after nu, given that you stop after the change point, what is the detection delay? What is n minus nu plus? So this is just how much did you take to stop, okay? So here's a simpler version of the statement. So so suppose our baseline increments, this means our underlying E process that we are using is actually just a product of ln. So suppose the E process looks like this, okay, and ln is only a function of xn, okay, so like 1 plus lambda times x minus n or something like that. It looks like ln, and suppose the post change observations from Q, suppose in addition that they are strongly stationary. Let's say IID for simplicity, just to look at the expression for the detection delay. Okay, so then the detection delay for the Shiryaev-Roberts procedure, which is the first time at which our E detector crosses 1 over alpha, has this nice expression which is kind of what it should look like. You have log 1 over alpha as the first term, and the denominator is like a proxy for KL divergence. These are problems in which there's no reference measure, thing like that. It's like KL inf or like if you saw the numeraire, it's the minimum KL from some distribution outside to the class of distributions or something like that. So yeah, this is like a proxy for the KL divergence. If you're in the parametric setting and L1 was the likelihood ratio, then this is exactly the KL divergence. But we are in these kind of non-parametric settings, so this is like the proxy for the KL divergence. It's the right term that appears here, and then there's some second order term which I'm not sure is optimal or not, but so far I've kind of just focused on the first order term. I think it's already interesting when for these kind of non-parametric problems you can get the first order term correct. Okay, so this is when you know Q. When you don't know Q, remember what I said was like you do a mixture of E detectors. So essentially, because E detectors are defined through their expectation, any convex combination of E detectors is also an E detector. So just take a mixture that still controls the ARL. And so this can be used to construct both statistically and computationally efficient mixtures over pi. So in our that automatically adapt to this unknown Q. So in the paper in particular, we derive an E detector using a discrete mixture idea where the number of mixture components grows only logarithmically with time. So somehow what the intuition is that you're looking at script P versus this very rich script Q, but when you have very little data, you can only detect far away alternatives, and as you collect more data, you can detect closer alternatives and so on. So if you kind of if you add a mixture component to your E detector once every so often, you can detect nearer and nearer alternatives. So anyway, there's some reason, but essentially this is like like you want it to be computationally feasible. So if the mixture is not just one term of this kind, but remember that this depends on lambda, and what I would like is effectively to say I'm going to sum from I have some j mixture components from nj, and I'm going to sum these for some particular lambda j, and I would like it that the number of mixture components that I have does not grow too large with time. And so the idea is that somehow you can get optimal detection delays even when the number of mixture components that you're tracking only grows logarithmically with time. So at time step 10 you might only have 1 or 2 mixtures, at time step 100 maybe you have 3 or 4 mixtures, something of that kind. So if you have a mixture Shiryaev-Roberts procedure, then this detection delay looks like the denominator is now like this KL inf between the true Q that you don't know and the class script P, which is like the reverse information projection type of idea. But the numerator is not exactly log 1 over alpha, but it's something that's very close to log 1 over alpha. So I don't want to go into this too much, but it's like essentially log 1 over alpha with a second order term which is log in some kind of strength, the signal strength that you're looking for. So it's kind of very close to log 1 over alpha, but because you don't know the signal strength that you're playing against, like let's say you're looking at the pre-change is mean is less than equal to 0 and the post-change is not separated, it's actually mean greater than 0. It's the script P and script Q kiss each other because the true mean could be arbitrarily close, the changed mean could be arbitrarily close to the pre-change means. There's some price that we have to pay which is log in the true mean. So that's what's coming up. So it's kind of a subtle thing, but you kind of get log 1 over alpha even though you don't know the Q. Okay, so here's the takeaway messages. This is what a script P E detector is. It's a non-negative process such that the expected value is controlled. This was an E process. This was the Shiryaev-Roberts procedure. Thresholding at 1 over alpha controls the ARL non-asymptotically. Mixtures of E detectors are also E detectors. And if you have these baseline E processes, they enable efficient online computation. And so now we can perform change detection in many non-parametric settings. Okay, so that's the kind of takeaway message of this part. Don't worry, the second part is much shorter, but let's take a break first. So maybe let's break for 10 minutes. That's fine. Let's come back at 4:20, and I'll show a much shorter reduction to sequential estimation, but for the non-partition change detection case, and then that should take only half an hour. So from 4:20 to 4:50, and then I'll end with about a 10-minute summary of game theoretic statistics more broadly. Okay, so. Okay, so pre and post change distributions are just simply two distributions in one single given class. Like for example, we just say I want to detect if the mean changed from something to something else, but I don't specify what that something and something else are. I just want to know if the mean changed. This is kind of fundamentally a different problem from the setting where I have separated them in advance. So this is joint work with my postdoc Shubhanshu, who's joining Michigan EE next year as faculty. And yeah, the TLDR is we can just reduce this to the problem of sequential estimation using confidence sequences. Okay, so the setup over here is we have some stream of it doesn't actually have to be independent, I'm sorry, but it's just you have a stream of x valued observation x1, x2, x3, so on, you know, for some capital T, xt is drawn from p0, and after t, here I'm using capital T for the change point instead of nu, it's drawn from some distribution p1, and p0 and p1 are both unknown, but we just know that they lie in some big class script p. So for example, all bounded distributions or all sub-Gaussian distributions, or you know, something of that kind, some big class script p, we just know they lie in that. And so we have to decide between essentially was there a change point or was there not, and we want to define a stopping time to declare a change that as we discussed before, average run length and small detection delay. And so the main point is somehow we need to specify, like let's say some functional that we are interested in detecting a change in. So you can say I want to detect a change in the mean, or I want to detect a change in the variance, or I want to detect a change in the distribution in the CDF, or I want to detect a change in the entropy. Doesn't matter, whatever. So you have to still specify what you're looking for a change in. It could be the whole distribution, that's also fine, but the idea is that if you can construct a confidence sequence for that functional, then you can detect changes in that functional. Okay? And so since the previous lecture was on confidence sequences, now we can just port all of those techniques here. And the reduction is very simple. It's almost identical to the e-detector, which is why I'm going to spend less time on it. But the idea is just at every time t, you start a new confidence sequence based on xt to xt plus 1 and so on, and we detect a change when their intersection is empty. So the intuition is very simple. So let's say I'm doing mean change detection. Let's say for simplicity Gaussian mean change detection or something like that. So I have some pre-change mean, let's say -5 that I don't know, and then at some point let's say it changes to some value like -2 that I don't know. And you know, that's the point of the change. So what I'm going to do is I'm going to form confidence sequences, and these confidence sequences are going to look visually like this. So you know, this is one confidence sequence that I have. Okay, that's the one starting from the first time step. Then the next confidence sequence that I have is, you know, is going to look like this. Then the third confidence sequence I have is going to look like this. So like I'm going to construct these confidence sequences, and it's actually going to keep going on, right? I mean, so after the change point, actually these confidence sequences will start to do something funky, like they'll do something funky after the change point. And then after the change point, I continued. I mean, I don't know the change point has happened, so I continue to form new confidence sequences. But these confidence sequences will be centered at this quantity. That's what they look like, and then the next one will look like this. So at each step, I just spawn a new confidence sequence going forward, and as soon as I find that there's some, so let's say at this point I find that this confidence sequences are over here while these confidence sequences were over here and they don't intersect, so I can declare a change point. So essentially, as soon as the intersection of all my started confidence sequences is empty, I say there's been a change, because some confidence sequences are saying the mean is here, some other ones are saying the mean is here, I declare a change. That's it. Yeah. The mean of it doesn't have to be the mean. It could be any functional. Theta is any functional you're interested in detecting a change in. Theta could be the variance, theta could be the CDF, theta could be the entropy. And the question is, can you construct a confidence sequence for that functional? If yes, then you can do change point detection for that functional. And it turns out that, yeah, I can construct confidence sequences for the entropy of a distribution, for the CDF of a distribution, for the median of a distribution, for the mean of the distribution. So yeah, theta is just any functional that you're interested in detecting a change in. Got nothing to do with means. And same way in the previous part of the e-detector, script P and script Q were just two sets of distributions. The type of change could have been in the median, in the distribution something. It had nothing to do with the mean. So any functional works. And the entire distribution, your functional could be the entire distribution. You can just say, I want to detect any change in distribution, and that's also fine. Okay, so the key fact is this method controls the average run length at 1 over alpha. It's like it's 1 over alpha. So you have 1 minus alpha confidence sequences, and you get average run length at level 1 over alpha. So I think it's very cute that this is non-asymptotically valid at that level. You don't get any other weird constants here. You get 1 over alpha. That's nice. And the second theorem is that somehow if the confidence sequences have minimax optimal width, then the detection delay is minimax optimal too. So for example, like if your confidence sequences shrink like square root log t by t, I'm hiding the log in the O tilde factor, like if they shrink like 1 over root t, then you can show that the detection delay that you have for your confidence sequence for this method is also minimax optimal. Okay, so that's just cute. Okay, so for the average run length, we have no assumptions. It just is 1 over alpha. For the detection delay, there's 2 assumptions, and I'll tell you why you need those assumptions. They're very mild, but you need them. So we're just dealing with some class of distribution script p theta. Here theta actually need not be a finite dimensional parameter. Like actually it could be parameterized by some infinite dimensional object. That's fine. In fact, as I said, theta could be the distribution itself. This is just for ease of notation. And then you have some metric over that infinite dimensional theta. Okay, so you can talk about the distance between 2 distributions that have parameter theta 0 and parameter theta 0. But the parameter is not a one-to-one mapping of the distribution. So there's many distributions with the same median. So if you're detecting a change in the median, theta could be a mapping from the distribution to its median, but many distributions are mapped to the same median. There's no problem over here. We're just looking for the distances between the changed median. Okay. So the first assumption is that your confidence sequence should have uniformly decaying width. Okay. So the uniform part is just that no matter which distributions I'm looking at in my class, the width should really be going down, and I should have a width upper bound that depends on the class script theta and depends on alpha. So this makes sense. My confidence sequences should shrink, and the limit of the width of the confidence set should be 0. So in the sense of if I get infinite data, it should have 0. I mean, I should identify the parameter exactly, kind of thing. So this is really satisfied for all the confidence sequence we actually know how to construct. So this is just decaying width. And the second point is there needs to be enough pre-change data. This is also kind of obvious. So let's tell you. Suppose I have a Bernoulli problem in which the first coin is Bernoulli 0.2. And then every other coin is Bernoulli 0.3, there's just no hope of detecting that there was a change, because I'm not telling you anything about the pre-change distribution. I'm saying it changed from some Bernoulli P1 to some Bernoulli P2. Well, if you saw almost no data from the pre-change distribution, how can you detect the change? So essentially that like this, the change between theta 1 and theta 0, let's call that delta, this distance metric between theta 1 and theta 0, I should have seen, if there was a change, then this change point t has to happen after some point where I've seen enough pre-change data, right? So that's all it's saying. So essentially if the change is large, then I need less data. So suppose it's the Gaussian mean is changing from minus 100 to plus 5 billion, then I need only 2 data points at the start which are around minus 500, and then it changes to plus 5 billion, it's totally fine. But if it changes from minus 1 to minus 1.1, okay, maybe I need a few hundred data points before the change. So like somehow the number of points I need before the change occurs depends on how large that change is. So that's also a necessary condition in some sense. So we need those assumptions, but under those 2 assumptions, we can prove a bound of this type, which essentially is saying that it's slightly different from the detection delay that I presented earlier, but there's a good event, which is the event that these confidence sequences cover their true parameter. So these confidence sequences with probability 1 minus alpha, every interval you construct covers your true parameter, but with probability alpha they don't. So the good event is a high probability event with probability 1 minus alpha. So the good event is saying that before time t, your confidence sequences did actually contain your true parameter, and if our width is like square root log t by t, like it often is, then the expected detection delay conditioned on the good event looks like log 1 over delta by delta squared, and there's a log 1 over alpha term as well, where delta is the amount of the change. And so this is the optimal scaling. This is really true for any WT going to 0. So this is the intuition for the detection delay analysis. Essentially, like just after the change point has occurred, you have some uncertainty about the pre-change parameter theta 0. You have seen capital T data points from that distribution theta 0, and that's the width of the confidence sequence so far. And then it is changed to something which is theta 1, and so you have some even more uncertainty about theta 1 since you have seen very little data from it. So just after the change point, this is the situation. This is the first set of confidence sequences have that width, and the second set of confidence sequences which you've spawned out have that width. And then, but as you continue collecting more data, the confidence sequences that you started after the change point, they'll continue to shrink, and then at some point, the original confidence sequences that you had that started at time 0 and the confidence sequences that you had that started at time t, you don't know which one they are, but they will not intersect anymore, and you'll declare a change point. And so it's kind of very easy to analyze the detection delay because you declare a change point exactly when the sum of these two widths, when wt plus wt minus t is the distance between them. So that's exactly when you do it, and so you can just solve kind of pretty directly for when you're going to stop. So it's because you have an idea what these widths look like. They look like square root log t over t. You know the constants also often. Like we have explicit constants, so you know exactly kind of when this will stop. So you can do this fully non-asymptotically and give a bound on the stopping time, but I've just told you it will roughly scale like log 1 over delta plus log 1 over alpha by delta squared, which is the right scaling of the detection delay. So yeah, as I said, so now you have applications to, let's say, mean shift detection with bounded observations or changes in the CDF, because I showed you that we have these confidence sequences for the entire CDF. So if the CDF changes and you just want to know, I don't know what the pre-change distribution is or the post-change distribution is, I just want to know if the distribution changed, that's it. Then that's fine. The theta I is the entire CDF of the distribution, and you can just use the Kolmogorov-Smirnov distance, and we have confidence sequences for that quantity, and so you plug that in and it works. And same with change, like similarly to sample change detection. So like if here it could, like you could have, it need not, so like in the earlier case it changed from two identical distributions to two different distributions, but now you could just say I have some two distributions P and Q that are already different from the start, and after some change point they move further away or they move closer together or something of that kind. So the metric, which is, let's say, the maximum mean discrepancy or the total variation distance or the Wasserstein distance between P and Q, that changes. You can say I'm looking for a change in the Wasserstein distance, I'm looking for the change in the MMD or the KL divergence. It turns out we have confidence sequences for the Wasserstein distance, for the MMD, for the KL divergence, so like for the total variation distance in discrete settings. So you just plug those confidence sequences in, and then you can detect whether there has been a change in the value of the TV distance between those distributions or something of that kind. And so you can do like regression, you can ask for, is there a change in the regression parameter? So I might have a regression problem, and I might, let's say I have the way y depends on x, y is beta 1x for some time, and then y is beta 2x after some time, and I don't know beta 1 and I don't know beta 2, I just want to know if beta 1 changed to beta 2 or not. Totally fine. If you have a confidence sequence for beta 1, which we do, so there are papers with confidence sequence for beta 1, you plug that into here, and you'll get this change detection. So the goal over here at least is, I don't know, it might be possible in particular instances to take that instance and study it really well and get something optimal, something even better. But the aim over here is, if you had 5 minutes and somebody gave you this problem, you can just do something straightforward which will just work. Like the point of a reduction is, it just works broadly. You get an answer in 5 minutes, and then you can spend a few months improving that answer if you want to. But if you just want something to work out of the box, this will work out of the box. Okay, so let me just summarize again the two parts of the change detection problem. For E detectors, we had separated classes. For the confidence sequences, we did not have separated classes. For the E detectors, we reduced it to sequential testing using E processes. Here we reduced it to sequential estimation. We spawn a new E process at every time step t. Here we spawn a new confidence sequence at every time t. We stop when the cumulative evidence crosses 1 over alpha. Here we stop when the intersection is empty. In both cases, non-asymptotically, uniformly over those classes, you get average run length control being at least 1 over alpha. And in both problems, you get near optimal detection delays. but at least non-asymptotic control over the detection delays in both settings. And so now, since sequential testing and sequential estimation are such basic problems, and we're getting increasing tools for those problems, you can port them now to sequential change detection. That's basically the goal here. Okay. Any questions about either of these? Yeah.
I have a quick one. So I was trying to think of an example that doesn't neatly fit into either of these two families. If you take your NBA, I mean, it's a bit contrived, but I'm going to describe it anyway. So if you think of your NBA example, and you were kind of testing a change from win probability less than equal to half to greater than equal to half, what if you didn't know which of those situations you were in at first? Then
no, but you said you're detecting less than equal to half to greater than half. So like it only makes sense to say that if your pre-change is less than equal to half. So
what if your pre-change was one of the? What if you're just trying to detect a change
from one to the other,
side?
from one side to the other
And
side.
the reason it seems to not fit in the first framework is because you don't know where you started, like you don't know script P.
Yeah.
And the reason it doesn't directly fit in the second case is because everything you're describing seemed very point to point.
Yeah.
So I'm curious, like, is there a way to handle those types of cases?
Yeah, it's a good question. I don't know off the top of my head, but I'm going to guess that one of these two methods might work, which is I'd have to think about it more. So it's like you do have script P and script Q, but you don't know which one you're in first.
Right.
Okay.
I mean, maybe you could, maybe you could solve that testing problem first. Like
Yeah. Maybe just spawn an E detector for both, and then whichever one rejects first, you crosses 1 over alpha first, you detect that change. Yeah. And then probably my guess is the ARL will be at least 2 over alpha. 1 over 2 alpha, something of that kind. So like I think that something like that should probably work.
Just understand once again the statement. You have two samples, you don't know which one.
Did you see the E detector part of the talk?
Yeah, so no, I mean it's precisely about your question.
Yeah. So I'm saying her question is take the E detector part of my talk and then say that I have two classes, script P and script Q. In this part of the talk, I said the pre-change is script P and the post-change is script Q. And she's asking, what if the pre-change is one of them and the post-change is the other one, but I don't know which is which. That was her question. So there's a twist on this.
We have a paper on this without the manipulation to detect.
Yeah.
And like the overall topic.
Yeah.
About testing pre-change, but I can show you.
Oh, interesting. Yeah.
Simon Daoud, so it's an interesting point.
Yeah.
In fact, there is a postdoc of Sasha Rapian who they were doing very similar stuff.
For change detection.
No.
Ah.
Precisely unrelated to change detection,
Oh.
but related to her question.
Her question was change detection.
Yes, but
Oh.
it's kind of put in the context of change detection. You don't have to group in change detection.
You
Just
put in the
consider a general problem.
Yeah.
Let's say two samples.
Yeah.
Okay.
But are you trying, what is your criterion? Is it testing then, type 1 error or?
Yes.
Or testing? Okay, so in the context of testing, I see.
The
Okay.
testing is hypothesis.
It's testing, okay, got it, yeah.
Hypothesis is a special way. So we can discuss it. But like that's. It seems that what you're asking.
But in
about-
testing,
Testing, it seems different.
yeah, I don't know. I don't even know how to. I don't know how to describe the I don't even know how to think about the problem in testing. If you're in one, it never changes to the other, right? Like it just stays in one. In testing,
Pair of distributions that that's correct. You know both of them.
yeah,
Okay, but let's say you don't know. Now you're shown. Let's say. Okay, sorry, I remember. So basically, you have. It's similar to two-sample testing.
yeah,
So in two-sample testing, you try to understand whether the two samples come from the same distribution or not. You have two samples now, but instead of just asking whether they come from the same distribution or not, I know that there is a pair of distributions. I know which ones.
so you want to match them.
And I want to match the right permutation upwards.
I see. That's I think that's very different from the question she asked there. But it's an interesting testing problem, but I don't think it's the same question. Yeah. Okay, so I want to spend the last part just summarizing again at a high level what game theoretic statistics is, which the summary will make more sense now. But it's basically a subfield of statistics whose quest is to quantify uncertainty in statistical inference tasks like 3 ones we saw today: hypothesis testing, estimation, and change detection. But why stop there? Probabilistic forecasting, model selection, things like that, by using game theoretic intuition, language, and formalism. Why would we want to do this? Because it helps us define new non-parametric inference procedures which have stronger theoretical guarantees under weaker assumptions. So this part we saw a lot in the previous lecture where we were able to achieve this quite generally. It provides greater flexibility in applications because you don't have to pre-specify sample sizes, you can continuously monitor your data, things of that kind. It combines Bayesian and frequentist views. You're allowed to use prior knowledge. The better is typically allowed to be a Bayesian. The guarantees are frequentist. The observer has frequentist guarantees. The actor is typically Bayesian. So optimal gambling strategies are typically Bayesian, but no matter how you act, the guarantees you get out of the framework are frequentist. So it's a nice middle ground between the Bayesian and frequentist paradigms. And they're kind of, the whole point about the game theoretic part is when you play a game, it's very natural to be adaptive. You know, if you played chess, you would not play the same against your neighbor as against Magnus Carlsen. You'll play differently against them. And if you don't know who your opponent is, you'll try to learn who that opponent is. And if they seem to be a very naive opponent, you can play aggressively. And if they seem to be a good opponent, you can play a little bit conservatively. And so this is very natural in a game that is how you will play games. And so that's how our statistical inference procedure should be. Our statistical inference procedure should be adaptive to the underlying difficulty of the problem. I should not need to know much about the underlying difficulty. I should have these general non-parametric classes with gradations of difficulty between them. So for example, I'm interested in the mean, but maybe I don't know the variance, but I know that the harder the problem is, the larger the variance is, the harder the problem is. But I should have procedures that can adapt to those kind of nuisance parameters automatically, and somehow thinking about it game theoretically gives you a very natural way of adapting like for free. So if you want to design adaptive procedures, then I think thinking this way helps a lot. So there's 4 characters in this sequential anytime valid inference story. 2 of them are real valued measures of evidence. So I defined these in the first lecture. You have these E processes, which I've defined again now, but you have also these P processes, which are in the P value scale. These are real valued measures of evidence. They don't have thresholds associated with them. But there are other notions which are associated with the level alpha. So you have 1 minus alpha confidence sequences, and you have sequential tests which have a level alpha. Okay, so these are the 4. These are called power 1 sequential tests. My emphasis, what I think is a central object, are E processes are the central object, and kind of understanding their properties or designing good or bad E processes, finding optimal E processes has been the focus of my research for many years now. But the good part is you can transform between P processes, between all of these concepts, and I'll just briefly spend some time on this. If I give you an E process, if you threshold at the level 1 over alpha, you get a level alpha sequential test. If I give you a family of level alpha sequential tests, you can invert it to get confidence sequences, and we saw that today morning when we did this betting framework. We wanted a confidence sequence for the mean. We really constructed a family of sequential tests by betting, and then we inverted that family. Confidence sequences and P processes are duals. P processes are for testing. This is for estimation, but these are duals. So essentially, I don't know if you're familiar with the duality notion of confidence intervals and P values, but that carries forward to confidence sequences and P processes. So you can define a P value at any time t as the smallest alpha for which the confidence a sequence that you have intersects the null hypothesis. So essentially find the alpha at which the confidence interval just kisses the null, and that minimum value of alpha is actually a P value. So you can move between P values and confidence intervals. If you threshold a P value at level alpha, obviously you get a level alpha sequential test. If you take the E process and you take 1 over the running supremum, you actually get a P process. So that's one direction. That's actually by Wheel's inequality, and it turns out you can go the other. If I give you a P process, you can do something called calibration and get an E process. So all of these concepts are tightly connected, and you can move in between them. But the way I like to think is E processes, which are non-negative super martingales or non-negative martingales, generalization of likelihood ratios to non-parametric, that's the real key object. From there you can move easily to these other things, and it's fine. So that's I think, and I think it's a nice new general definition, and I think people should pay more attention to that. I want to end with some thoughts about non-negative martingales. We know that every likelihood ratio is a non-negative martingale with initial value 1. But I've been kind of claiming informally that non-negative martingales are also like they're proxies for likelihood ratios. But there's a very formal sense in which every non-negative martingale is implicitly a likelihood ratio. And here is that formal statement. Okay, so if I have, so remember, test martingale is a non-negative martingale with initial value 1. So if I have a composite test martingale, which means the same process MT is a martingale under every distribution in script P. So we saw that in the bounded mean testing example. Then for every P, we can write MT. Okay, so this is meaning that my process MT is simultaneously this process MT, which is a non-negative martingale for script P. It's actually equal to Q1 divided is actually whatever dQ1 by dP1. It's also dQ2 by dP2. It's also dQ3 by dP3. So like for every P, in my class script P, my process MT is simultaneously a likelihood ratio for all of the. It's like it's a remarkable fact. So this is a very formal sense in which non-negative martingales are simultaneous likelihood ratios. So this might be the case that even though I might not have a dominating reference measure for script P, this fact is actually still true. The Q will be absolutely continuous with respect to P for this fact to hold true, but nothing that I didn't need IID structure for this. I didn't need any structure for this. This is a completely general and correct statement as written, no assumptions. If I have a non-negative test martingale for script P, it is a simultaneous likelihood ratio. So this is why I think that these methods are so powerful. We know that likelihood ratios are at the center of parametric inference for 100 years. Whether you're a Bayesian or a frequentist, likelihood ratios are your go-to thing for parametric inference. But I claim that they're also at the center of non-parametric inference. We've just never known how to get at them, and the answer to get at them is don't try to construct likelihood ratios, try to construct non-negative martingales. And e-processes generalize these non-negative martingales significantly. They exist more generally. What do I mean by they exist more generally? There are problems for which non-negative martingales don't exist. So I'll give you some examples right now. I kind of have spent some time like dividing the set of all testing problems into 3 classes. So the first class is testing problems for which test martingales do exist. I mean non-trivial ones, which means under the alternative they go to infinity, under the null they are test martingales, under the alternative they grow large. So if I'm testing symmetry or 2-sample testing, I'm testing for bounded means, things of that kind. And these are all problems with no reference measure, but still non-negative martingales exist. There's some interesting ones. For testing exchangeability, there's no test martingale in the full filtration, but there is a test martingale in a reduced filtration. Similarly for independence testing, and similarly for the t-test. You can prove this. You can prove that for some problems there is no test martingale in the original filtration of the data. You have to shrink the filtration of the data, then suddenly test martingales emerge. But there are some problems for which no non-trivial martingale exists, but non-trivial super martingales exist. So for example, sub-Gaussian distributions or any bounded MGF, you can prove that there is no test martingale for sub-Gaussian distributions, but there are test super martingales. We saw those. And then like things like robust heavy-tailed mean estimation, you can prove that no martingale exists, but super martingales exist. And then more generally, there are yet other problems for which you can prove that no test super martingale exists, but e-processes exist. Okay, and so any composite null for which likelihoods exist, you can do universal inference. If you have a t-test and you have the original filtration, you can define an e-process. If you're testing exchangeability in the original filtration, you can use e-processes. So anyway, so there's some subtleties over here about the filtration, but essentially all testing problems can fit in this framework, and I've given you some subset of them that I've studied. But I think one interesting part of the story is that every testing problem that is testable with the game theoretic framework. This is not a restriction in any way. Like if you can test it, you can test it using e-values or e-processes. If you can sequentially test it, you can test it using e-processes. So e-processes are necessary and sufficient for sequential testing. This is you can establish this formally. So you don't lose anything by thinking game theoretically. In fact, I suggest you gain something. And yeah, so I think making a complete story of this is still open, meaning we don't fully understand why this separation occurs. There's something called fork convexity, which is a geometric characterization which separates these things. So for example, if you have a fork convex null hypothesis, then test super martingales could exist, and so anyway, so there's some geometric, but we don't have a full story yet. So in the coming years, I'm hoping to study that full story. So if you're interested, here are some current and future directions for a completely new non-parametric problem that I throw at you that you've never seen before. How do you design the game? Remember, I told you that the game design is not unique. So in fact, for independence testing, I have 2 different games, one in the original filtration, one which throws away data, And similarly for exchangeability, similarly for the lady tasting coffee in the first lecture, we have many games. And so for a new problem, how do we design the right game, and how do we learn how to bet in that game? Can I make this more systematic? Right now it's halfway between a science and an art. Like this exponential class of super martingales is a nice one to go to, or this product of 1 plus lambda times is a nice one to go to, but like, can I do something more systematic? So then there's this question, which is, can I fully characterize when do non-trivial test martingales exist or not exist, when do non-trivial super martingales exist or not exist, and when do non-trivial E processes exist or not exist? So the answer for this question, I believe, is whenever there's a sequential test, there's a non-trivial E process. So this which means the answer to this is it possible to test? If it's possible to test, there's an E process. So I think this one will be simple, but the separation between these classes I don't know yet. How do we go beyond today's topics, this tutorial topics, to say game theoretic model selection? Okay, so I have some ideas. We have some preliminary work on it, but I don't have anything systematic. It would be nice to see something systematic. Systematic meaning really a general reduction kind of thing. Everything today yesterday and today was non-asymptotic. So you can ask, what does it like? There's a lot of statistics, more generally classical statistics, that's based on asymptotics. And can I develop a theory of anytime valid asymptotics? And the answer is yes. So we have a paper on what's called time uniform central limit theory. So it's like an analog of the central limit theorem for a time uniform version. It's a universal, like the central limit theorem is a universality result, right? It says I don't need to know more than the mean and the variance from the distribution, and then I can tell you how every average behaves. So it's the same kind of result, but the central limit theorem is really for a large fixed sample size. What is the analog of the central limit theorem when I want to peak continuously at the data? So anytime valid, so the title of the paper is time uniform central limit theory. And so we have some ideas of how to extend all of this stuff to asymptotics. It's starts to get quite subtle. And I think the last kind of big open problem, which I didn't discuss before, was how do we tie game theoretic statistics together with game theoretic probability? So game theoretic probability is an approach to probability that does not use measure theory and uses like entirely game theoretic principles. I've been talking to a lot of people about this bridge, but essentially I love game theoretic probability, I get inspired by it, but then I write my game theoretic statistics papers in measure theory. Part of the reason is I don't think people know game theoretic probability, so if I was to do this in a game theoretic probability language, nobody would understand what I was doing. But another reason is that it turns out that when you work with game theoretic probability, you have to start with a set of gambles and not a set of distributions. You've started the set of gambles, and the most efficient way I know how to describe a set of gambles is to describe a set of distributions and say it's all the gambles that are consistent with the set of distributions. So I don't know otherwise how to represent a set of gambles efficiently to work with game theoretic probability at scale. So there's some kind of, so I think I would like to see more work at the intersection of those two fields. Right now I've been mostly an observer of game theoretic probability and a contributor to game theoretic statistics, but I think there's more work to be done at that boundary. To make it really fully game theoretic, and then there's online learning, of course, which is game theoretic learning, which fits into this quite easily. I haven't talked about it, but online learning has connections to game theoretic statistics and game theoretic probability, which is also interesting. Anyway, so these are some current and future directions for people who are interested in this area. I should stop and thank my various collaborators over the years. It's too many people for this one slide, but I'll share the slides later on and you can have a look at them. But the top row are basically various faculty at various universities who are my co-authors, and these are my various students over the various years many who have graduated and are now at various places who have worked with me. So so a lot of work would have been impossible without this set of amazing people to do it with. Okay, so with that, let me stop. Thank you for your attention and time. I'm happy to take more questions.